Hello, good morning to you all. And as I was discussing the part 1 of the radiophysics for the exclusively for the PGTs in radiology, and so I will be starting again from the part 2, that is half-life and the mean half-life of the radioisotopes. And as we have talked already, that is half-life, definition of half-life, and it is the radioactive element defined as the time taken for the half an integral number of atoms to disintegrate. This is actually the definition of half-life. And from the law of radioactive disintegration, the fundamental equation is n is equal to n to the power, just a minute, it is equal to n to the power 0 e to the power lambda t. So if the t half-life is half-life, then if, for example, the t half-life is half-life only, then the small t is t half-life, n equal to n0 by 2, and substituting the above equation, we can get the t half-life, we can replace the t half-life by n0 by 2, and that is equal to n0 to the power e, n0 e to the power lambda t half, and that is half by t equal to the e to the lambda t by half, and that is, if you substitute the equation, that will be equal to 2 equal to e lambda t by half, and log e 2 equal to lambda t half, or t half-life is equal to log e to the power 2 by lambda, which is equal to 693 point lambda. So actually this is the disintegration equation, and I think this equation it is not so important, but you have to remember this. And the half-life of the radioactive element is inversely, now you have to discuss about the half-life, and half-life of the radioactive element always is inversely proportional to the decay constant of that element. So it is seen that after one half-life activity it is reduced to half value. 2 half-life, it is 1 by 2 to the power square, that is 1/4, and after n half-life period it is equal to 1 by 2 to the power n. So it is inversely proportional, and half-life value of the important radioisotopes, which I had already given in the earlier video, like for example the radium is 226, cobalt is 60, etc. Now in general, the decay of all radioactive element will take the indefinite time. However, the imaginary concept of one definite mean half-life, or which is mathematical definition as tau, for example radioactive isotope, mean life refers to an average life for decay of all radioactive items for radioactive atoms, and mean life refers to an average lifetime for decay of all radioactive atoms. Now it is defined as the lifetime of imaginary source which decays at the constant rate equal to an initial activity produce same total number of disintegration and is exponential decay. Okay, so the mean half-life is related to half-life as, so the always this is a very important concept. The mean half-life is equal to the half-life as tau is equal to 1.44 t to the power to the power half, so that mean half-life is directly proportional to the half-life, and it is always longer than the half-life period and finds application in the radiation dosimetry. So in 3D image reconstruction, multiple frames are needed. During an acquisition of counts for image frame, radioisotope undergoes decay, and if a image acquisition time is not small compared to half-life radioisotope, then the image frame decay correction is started. Example, FDG imaging of the PET CT, and if image frame acquisition starts at t second and end at t plus delta t, which is the change of the t second, then the effective decay factor is given by the df equal to df in bracket t into 1 into e to the power minus x divided by x, where dft is the decay time and t and small x in2 into delta t into the t to the power half. Now this is the mathematical expression which is given in your radiophysics textbook, and you have to understand the half mean life and the mean life period. So half mean life, they can ask you about the short note in the half life and half mean life of the radioisotopes, where you can give the equation. And as I told you, the half life period of the few radioisotopes are like radium, cesium, cobalt, their years and their days. So this is the important time, concept. Now effective half-life. Now what is the effective half-life? Effective half-life is the physical half-life time required for a radionucleotide to decay to the half of the original activity, and it is expressed in relation of the T half-life, which is equal to the 0.693 to the lambda, where lambda is decay constant, and half-life, that is TB, is determined by the clearance ratio nucleated from the organ or tissue, and effective half-life T is the radio of multinuclear organ of the both radioactive decay and biological decay, and the relation between the effective biological and physical half-life, that is effective, which is determined by the equation 1 by TE, biological 1 by TB, and the physical half-life and given by the T half. It is a formed by equation is equal to 1 by TE equal to 1 by TB plus 1 by T half. So this you have to remember. For example, I am telling you an example that a numerical can be asked, or you can give the example of a numerical while we will be defining the half-life and the median half-life or disintegration constant like this. Like for example, a radionucleotide has a physical half-life of 6 hours. Okay, a radionucleotide has a physical half-life 6 hours and a biological half-life of 3 hours. Then 1 by T is equal to 1 by 6. Okay, because 6 hours is the biological half-life, so it will be the 1 by TB is equal to is 1 by 6, and the half-life is 3 hours, because it is already written that 3 hours. Then the total effective the TE effective half-life will be 2 hours. So the effective half-life is always lesser than the biological half-life. Always remember, the biological half-life is always less than of the effective half-life, which is lesser than physical half-life. Okay, so these are the effective half-life, and after that we are coming to the activity. Now what is activity? Activity is rate of the activity of the radioisotope is an activity of that isotope. The decay equation is multiplied by the lambda, where A is equal to lambda n to express the radioactivity of the isotope, and A equal to A to the power 0 E to the power lambda T, where A is the initial activity and A is the activity time T. Activity number refers to unstable nuclei that remain stability through radio disintegration per unit time. This information is significant as the quantity and radiation released from the radioactive material is directly proportional to the activity. So the activity gives an idea about the quantity and concentration released per time disintegration rate from the radio source. So this is actually the activity, the activity of that particular radioisotope, and it is always expressed by a formula which is equal to A, which is equal to A to the A0 into E to the power lambda T. So this is actually the equation for the activity. Now if you plot the graph against the effective half-life function of biological and physical life from the two-dimensional X-ray, and in the x-axis you will give time, and if you give the change radioactivity in percentage in the y-axis, you can see the physical half-life is more than the physical half-life comes down as a slow, then biological half-life, and then effective half-life. So effective half-life changes rapidly in the time with respect to the original decay, then biological half-life, and then physical half-life. So that has been already, I have explained the relation between the TE plus TB plus T half. So that you have to remember. Now we are coming to the units of activity, that is also very important. The disintegration rate of the radioisotope is measured by the unit of Becquerel, and Becquerel is the SI unit of activity and equal to the 1 disintegration per second, which is known as the DPS. In practice, megabecquerel and gigabecquerel are used as units. Is 1 MBQ is equal to 10 to the power 6 BQ, and 1 GBQ is equal to the 10 to the power 9 BQ. Okay, so this is actually the relation, and this relation you must know. And the special and the old unit of activity is Curie. The special and old activity is Curie, and 1 Curie is equal to the number of DPS from 1 G of radium, that is Ra226, and found to be 3 into 7 into 10 to the power 10 DPS. DPS means disintegration per second, and smaller units such as millicurie, MCI, or microcurie, or nanocurie, and picocurie are also used as unit. For example, 1 millicurie is 3.7 into 10 to the power 7, that is equal to 37 MBQ, and 1 microcurie is equal to 3.7 into 10 to the power 4, that is 37 kilobecquerel. So in this way we define the unit of activity and the unit of Becquerel and Curie is related to 1 Becquerel is equal to 2.7 into 10 to the power minus 11 Ci, and 1 Ci is equal to 3.7 into 10 to the power 10 Becquerel, which equals to 37 GBq. That is giga Becquerel. So since the activity deals with the number of emission, it does not have any practical application in diagnostic. Now you have to remember that these are only for the theory purpose. Now in diagnostic radiology, we don't have any implication of these particular equations or in particular theory. So in theory they can ask you, but in practical, in diagnostic radiology, when we are diagnosing it, particularly for a particular disease purpose or when we are seeing any CT or MRI, it does not have any implication. And these units does not tell us about the dose delivered to the biological system. Hence new quantities like exposure and absorbed dose are defined. So absorbed and absorbed dose are only defined, and specific activity like as defined as the activity per unit time, and it is unit is BQ kg to the power minus 1, and useful quantity in designating radio source in nuclear medicine and radiotherapy. And some miniature radiation dose can be made if the specific activity is higher. Radioisotopes may contain stable isotopes which are known as carrier, and radioisotopes without stable isotopes are known as the carrier-free isotopes, which may have higher specific activity. And if the radioactive elements is liquid, specific to the activity is expressed in the activity per unit time, which is equal to mb qml to the power 1. This is very useful to calculate the activity to the injected patient for non-imaging study, and it also gives an example information about the precise presence of the carrier, that is non-radioactive material of the example. Now, so if I give you an example like iodine, the atomic mass is defined as 131, and the radioisotope having half-life of 8 days, for example, and which is used as iodine therapy in thyroid ablation as the initial activity of 100 microcurie, and what is the remaining activity after 10 days. So here the A0, as I already told you, what is A0? A0 is actually the initial activity. So here the initial activity is 100 mi, and the half-life is 8 days, which I told you. So the T half-life will be, as the formula is suggested, 0.693 by lambda. On if we take out the lambda will be 0.693 divided by T half-life. So 693 by T half-life is the 8, which is equal to 0.0866 days to the power minus 1. And if we take out the A, so A will be, I think, the decay equation multiplied by A, where A is the activity at time. So here what is the remaining activity? So here the question is asking about the remaining activity after 10 days. So AU, the equation is A0 e to the minus lambda t, which is 100 mi into 2 to the power minus 0.0866. So here lambda t, the lambda t which we have already taken out, that is 0.0866, that will be in the power 10 to the power MCI into e to the power minus 0.866 into t. That is already the equation, and then we can find out the initial decay time. So initial decay time is 42 microcurie, and this includes both physical and biological decay. So this you have to remember the formula. What is the formula of T half-life, and how to calculate the lambda, okay, and how to calculate the initial activity, which is known as A, and A0, which is known as initial activity. So this is always given by the formula lambda t. So here you have to remember the A equal to A0 e to the power lambda t, and the lambda t is always equal to 0.086 into the power 10, because why 0.086? Because it is here it is equal to 0.086 0.0866 days to the power minus 1. So if we are converting it, it will be go to minus 0.086 into 10. So it will be 48 millicurie, and this includes physical and biological decay. So this is the more important part, and it can be asked as a theory question to your exam in the in your final examination. Now we are coming to the radioactive series. Now what is radioactive series? Radioactive series, there are actually as we know that there are actually 103 elements in the periodic table. Element Z equal to 1 to 92 occurring naturally, where Z is more than 92 produced artificially. Elements of the Z more than 82 are unstable, as I told you earlier in the video, and said to be the radioactive. And there are three group of naturally occurring radioactive substance like uranium, actinium and thorium. The uranium starts from the U-38 as a half-life of 4.51 into 10 to the power 9 and undergoes a transformation with the emission of alpha, beta and gamma rays, and end of the lead 206. And radium comes from the above series in the fifth transformation with the lead 206. Radium comes from the above series after fifth transformation, and radium is converted into stable isotope, that is lead 206, and the actinium starts with uranium 235 as a half-life of 7.13 into 10 to the power 8 years, undergoes transformation and end up with the lead 207. And thorium starts from thorium 232 with half-life 1.39 with the 10 to the power 10 years, undergoes transformation and end with the lead 208. Now, so these are the radioactive series which you have to remember about uranium, actinium and thorium. And after that, this is actually, I think I have discussed, because I will be discussing it because this chapter is very high, much more, and this chapter requires always an conceptualized based, and since it is not a theory part, it also contains the mathematical part. So I will be discussing about the radioactivity and the gamma rays again as a part 3 of radioactive physics, of the radiophysics. And in the next chapter we will discuss about the nuclear transformation like alpha decay and alpha properties, with the beta plus decay, with initial conversion and the gamma emission, with nuclear bombardment and nuclear reactor or nuclear reactor principle, and production of radioisotopes. The production of radioisotopes are very important, which you have to remember by heart, and on the basis of this the equation or the questions are being formed, and then we will declare about the radiopharmaceuticals and different types of radiopharmaceuticals, and then we will start about the production of the X-rays, which we have discussed, and again we will discuss. So this is the part of the second part of the gamma rays and of radioactivities and gamma rays. And in the next unit we will start the next part of this chapter only, where we will discuss the different nuclear transformation, and then we will move ahead slowly. Okay, and if you have any question you can ask me. You first hear the video, and if you have any question then you can ask me in detail, so that I can give you in writing and in my group or in my WhatsApp group on personal. Thank you a lot.